Welcome to my talk. In this talk, I will be talking about automorphism groups of maps in linear time. So by a map, we mean a two-cell embedding of a graph on a surface, which means an embedding of a graph such that each face is homeomorphic to a disk. We study their automorphism groups, which are permutations of the vertices, which preserves incidences of vertices, faces, and edges, thus extending to a homeomorphism of the underlying surface. So we introduce a representation of a map which will be very convenient for us. This is an embedded graph on the sphere, and we choose a global orientation. And then you can see that each edge is split into two oriented edges called darts. And around each vertex, we have a cyclic permutations of the darts emanating from that vertex. And each two darts are somehow paired. I mean, all the darts are paired. So more formally, a map is a triple DRL, where D is the set of darts, L is some involution, and R is an arbitrary permutation. And the group generated by these two permutations is transitive, which means that the map should be connected. And in this language, the cycles of R correspond to the vertices of M. You can see that 1, 3, 2, for example, corresponds to this vertex here. The cycles of L correspond to the edges. So the edges are paired, the cycles are of length 2, and this corresponds to the edges. And the cycles of R minus L composed corresponds to the faces of M. So you can easily check that if you write out the cycles of R minus L, this will be exactly the faces of the map. So we study isomorphism. So a morphism is a permutation or just a mapping which respects these permutations, so it commutes with them. And a bijective morphism is an isomorphism, and we are interested in a set of all isomorphisms, or the automorphism group, which is the set of all isomorphisms from map to itself. So let me give an example. So here is a graph embedded on a sphere, and this is a star. So if you just consider it as a graph, you would have a lot of automorphisms. You could permute each every two leaves here. But if we have this as a graph embedded on this surface, then we really can only do rotations. So the group is cyclic. So here we have a similar situation. We have a cycle on the equator. So what we can do again rotations, but we can also swap the upper and lower hemisphere. So the group is dihedral. So then we also consider reflexibility. So the orientation reversing automorphisms. And here the mirror image is just obtained by inverting the permutations, and a map is reflexible if it's isomorphic to its mirror image. So the set of all isomorphisms, the full set of all isomorphisms, is together obtained by the orientation preserving isomorphisms and by the orientation preserving isomorphisms to the mirror image. Similarly, the full set of automorphisms. And the automorphism group, the orientation preserving automorphism group, is a subgroup of the full automorphism group, of course. So here is another example. So now if we consider the full automorphism group, we can also add reflections. So the automorphism group is slightly larger. And here we again add reflections. So the automorphism group is even larger than before. And in this case, it is a coincidence that it happens that the automorphism group is of such a map is in fact larger than the automorphism group of the underlying graph. But if the underlying graph is tree connected, this doesn't happen. So we are interested from computational point of view to find all isomorphisms between two maps, or to a related problem to find the full automorphism group of a map. So you can see that these two problems are related because, for example, if you want to find the set of all isomorphisms, it suffices to find the automorphism group and one single isomorphism between the maps. There is a trivial quadratic algorithm for this. So it is known that if you, for example, prescribe, if you want to find an automorphism or an isomorphism between two maps, and you prescribe an image for some dart x, then this must extend to a unique isomorphism, or it does not. So for a prescribed dart, we have unique possibility how to extend it. So and this can be checked in using a breadth first search. So this gives, in fact, a quadratic algorithm. The question is whether we can do better, and our result is that we give a linear time algorithm, which is parameterized by the genus of the underlying surface. So some related work was done by Hopcroft Tarjan and Hopcroft Wong. They gave some algorithms for three connected planar graphs, which are essentially maps, because by Whitney's theorem, a three connected graph has a unique embedding. A three connected planar graph has a unique embedding. So these are essentially the same problem as we are considering. So they gave a linear time algorithm, Hopcroft and Wong, and then in 1981, Colborn and Booth asked for a linear time algorithm for computing the automorphism group of a map on a sphere, and we of course do this in a much greater generality, and as a consequence, we also, one could say, simplify the Hopcroft-Wong algorithm quite a lot. So a related problem is a simultaneous conjugation problem. So in this problem, we get two sets of permutations, and we are asked to find permutation gamma such that all of these equations are satisfied for each I. So this is a generalization of our problem, because in our problem we have just d equal to 2, because map can be described by just two permutations, and gamma plays the role of the isomorphism. So this is a generalization of our problem, and uh, and so there has been known a quadratic algorithm for this problem for quite a long time, and only recently it was there was a faster algorithm appeared, and we can see what does this imply for our case. So if d equals to 2, we get an O(n) squared over log n algorithm for maps, which does not depend on the genus. But this maybe is not a significant improvement, and we believe that a truly subquadratic algorithm is not possible. So it's an interesting open problem to prove whether there exists, some conditional lower bound in the spirit of the fine-grained complexity. So if there would be a truly subquadratic algorithm for maps, some hypotheses must fail. So it would be interesting to prove something like this. So I would like to speak now about our algorithm. So the idea is to apply a small set of reductions, preserving the symmetries. So these reductions will be local, and we want to preserve the global symmetry of the map. So so for a given map, we produce some irreducible map for which we will be able to somehow compute the automorphism group, and it can be translated to the automorphism group, to the original automorphism group we wanted to compute. So what will be our defining property of the irreducible map? So it can be in the best way explained on the example. So what we want to achieve is to arrive to some kind of uniform map. So for example, for spherical maps, one can easily describe all the maps such that if you look around some vertex, then the cyclic vector of face sizes is the same for every vertex. So these are, for example, bouquets, which are just loops with one vertex, cycles, dipoles, which are just multi-edges between two vertices, prisms. Prisms we see here, the lower row, and antiprisms, which we see in the top row. So these are the infinite families of spherical uniform maps. So the cyclic vector of face sizes must be the same at every vertex. Then we have another type of uniform maps, which are in the first row there are Platonic solids, and then in the 13th row there are Archimedean solids. So these are not infinite families. These are some special cases, all of course very well known. You can see that around every vertex you have the same vector of face sizes. So for sphere, these maps can be described easily. And there is one more which satisfies this property, but we do not put them in this class because, in fact, this one is not vertex transitive. It's easy to check. It's called pseudo-rhombic cube octahedron. And for spherical maps, these are all the maps, all the uniform maps with this property that you have a local type, so the vector of face sizes at each vertex the same. So for torus, they can be also described, and they correspond to these 12 tilings, uniform tilings of the plane. So here are all of them. So the idea will be to reduce the map to cases like this. And for higher genus, in fact, one can prove, because here we have infinite families for torus and sphere, for higher genus, one can prove that the number of such maps depends only on the genus. So here is just a technical note. We'll be actually applying some reductions, and we will be in fact considering labeled maps. So we need to label the darts to preserve the symmetry, because if we do some reduction, it can happen that the automorphism group will be larger, because we can create some automorphisms, but we have to fix this by labeling. I will not speak about this anymore, but it's just a technical note to keep in mind that we are in fact working with labeled maps. So the first reduction is to get rid of loops and multiple edges. So this is the top priority reduction, and the point of this reduction is to get a face normal map, which means without loops and dipoles. And the motivation is that then we can apply Euler's theorem to get a bound on the minimum degree. For example, for sphere, it is 5. Then the main reduction, it's actually very simple, is that we consider the vertices of the minimum degree. So let's say that this vertex V is of minimum degree, and then we consider all its neighbors, and especially the neighbors which are of higher degree. So in this case, these are the vertices U0, U1, U2, and so on. So, and we transform it locally. We add this face here, bounded, defined by the vertices U1, U0, U1, U2, and so on. And these edges here are slided. So, for example, the block of the vertices of the same degree. So here are the vertices of the same degree as V, is just slided along in the counterclockwise direction. So A0 is slided to U0, A1 is slided to U1, and so on. So this can be defined formally in terms of the permutations, as I described in the beginning, and the automorphisms can be formally checked that the automorphism group is preserved by checking the commuting rules. This gives some work, but it can be really formally checked that this preserves the automorphisms. And it's a very simple reduction. So if we cannot apply this reduction, it means that the vertex of minimum degree has its neighbors of the same degree. So there is no vertex of minimum degree which would have a neighbor of higher degree. This means that the map is k-valent, or every vertex is of degree k. Okay, so how to proceed further? So at this stage, we can no longer distinguish vertices based on the degree. So we refine the procedure by using the local types instead of degrees. I've already mentioned the local types. So it follows that the number of local types is bounded. The number of local types that is sufficient to consider the same as degrees is bounded by some function of the degree. And it suffices to notice that our reductions do not really depend on the degrees of vertices, but rather on some vertex labeling, not related to the dart labeling, which is linearly ordered. So, so for local types, which can be also linearly ordered, a reduction can be applied in the same way, but instead of degrees, we use the local types. So this is a great simplification, and uh, at the end, if no reduction like this can be applied, we arrive to a uniform map which has all the local types the same. So uniform maps, as I described, for genus G0 and 1, there are infinite families of uniform maps. So for this, we actually need some additional algorithms. And for genus 2, it follows from the Euler-Poincare theorem that the number of such uniform maps is at most function of G, so we can brute force. Right. Here, I want to talk about the spherical maps, spherical uniform maps, and it turns out that the infinite families are reduced to the cycle isomorphism. I just want to recall how to test the isomorphism of colored cycles in linear time. So here we have a colored cycle, and in each step we find a pair of vertices that follows the orientation, which is of different colors. So like here, red, blue, red, blue, red, blue. We pick some pair, some colored pair, and we check all that pairs. Then we can notice that we can contract these pairs and introduce new colors, and this preserves the automorphism group. And then we get rid of those pointers which do not have a different color following the orientation. So for example, we get rid of this pointer and we get rid of this pointer. So we are left here with just two pointers, and we continue contracting until the end, until we are left with a monochromatic cycle. And for monochromatic cycle, we can easily determine the automorphism group. So for toroidal maps, we have several infinite families, so 12, and all of them are reduced actually to two cases, to the quadrangulation and to the triangulation of the torus. So to these cases, everything is reduced, and for these we again need some special algorithms, which somehow generalizes the algorithm for the cycle, but it's now much more complicated. So I don't have time for this here, but just to give some rough idea. So how do we reduce just to those two cases? So here we have the tilings, and basically we take the dual. And if we take the dual, it can be seen that if we take the dual, then we can again arrive to just one of those three cases, which is the triangulation, quadrangulation. Sorry, not this. Just these two cases, and for these we give a special algorithm. So just the last thing, I didn't talk about non-oriented maps, so maps on non-orientable surfaces. So recall that our representation of maps really depends on the orientation of the surface, because at every vertex, every vertex is represented by some cyclic permutation of the darts emanating from it. So we really are using some kind of a global orientation in the background, but this no longer can be done on a non-orientable surface. So, for example, here we have again a graph embedded in the projective plane in this case. So this is a K4 embedded in the projective plane, and now every uh, so now the map has to be represented in a different way, and it is represented by what is called flags. So these black dots represent a triple vertex, edge, and face. So if you imagine putting a vertex which is not depicted, putting a vertex in the center of this face, and then joining this vertex uh, to the middle of an edge, each edge of the face, and to each vertex of the face, then these black dots will be exactly in the centers of the triangles you obtain in this way. And we have some involutions, some permutations, which connect these triangles together. And these triangles are called flags. So in general, a map is defined like a four tuple, which is a set of flags, and three involutions, which satisfy this property. Again, we want it to be transitive, and because we want the map to be connected. So of course the maps on orientable surfaces can be represented in this way, but this is slightly more complicated. So for orientable surfaces we prefer the easier description where we make use of orientation. So in general, the input of our algorithm is given as this four tuple. Then we have to decide whether it's an orientable or a non-orientable map. If it's an orientable map, we construct the oriented map representation described before. And if it's not, we do the following. So um, we make use of so-called antipodal double cover. So for example, sphere is an antipodal double cover of a projective plane. Torus is an antipodal double cover of the Klein bottle, and so on. There is the relation between the genus of the non-orientable and orientable surface can be expressed which is the antipodal double cover of what. And it can be in fact shown that if we have a non-oriented map, we can construct the oriented double cover from the non-oriented map in the following way. And then there is a relationship between the automorphism groups. So the automorphism group of the non-oriented map is actually a subgroup of the orientation preserving automorphism group of the antipodal double cover. And now again, if the genus, if the map is not a projective plane or a Klein bottle, so the genus is higher, then we can brute force, because then the automorphism group is in fact bounded. This follows from theory of Riemann surfaces. And if it's a projective plane or a Klein bottle, we can transfer these automorphisms down to the original map, and we can in fact somehow, using some special algorithms which are again quite technical, and we are out of time. So with some special algorithms, the automorphism group of a projective planar map or a Klein bottle map can be also determined. So the final result is that there is an algorithm for a map, a general map, that finds the generators of its automorphism group in time parameterized by the underlying genus. in linear time parameterized by the underlying genus. So that's it. Thank you for your attention. I'm happy to answer some questions during the ICALP session.